In this part of your Security AI Plus journey, the fastest way to stop feeling lost is to build a simple map of what people mean when they say AI, because that word gets used as if it describes one thing. In reality, AI is more like a neighborhood with different streets, and security questions depend on knowing which street you're on. Sometimes a system is doing pattern recognition on past data. Sometimes it's learning complex representations from huge datasets, and sometimes it's generating new text or images based on what you ask it. Those are not the same, and the risks are not the same either. If you treat them as one blob, every scenario sounds confusing and every answer choice sounds plausible. If you can separate machine learning, deep learning, and generative systems in your mind, you'll start hearing security implications immediately. The goal here is not to turn you into an AI engineer, but to give you enough structure to reason clearly about what a system is doing and what could go wrong. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A useful starting point is to define artificial intelligence as an umbrella term for systems that perform tasks we associate with human intelligence, like recognizing patterns, making predictions, or generating language. Under that umbrella, machine learning, ML, is a major branch where systems learn patterns from data rather than being programmed with exact rules for every situation. The key word is learn, meaning the system adjusts itself based on examples, and that creates both power and risk. Traditional software can have bugs, but machine learning systems can also have weaknesses that come from the data they were trained on, the way they were evaluated, and the assumptions baked into their design. In security, that means you don't just protect code and infrastructure. You also protect data pipelines, model behavior, and the decision boundaries the model learned. When a question mentions machine learning, you should immediately think about training data quality, model evaluation, and what happens when real-world inputs don't match what the model expects. This is a different mindset from ordinary software, and the exam will reward you for recognizing that difference. Within machine learning, there are many model types, but you can keep it simple by focusing on the idea of features and patterns. A machine learning model tries to take inputs, often represented as numerical features, and map them to outputs like a label, a score, or a decision. For example, a model might take information about an event and predict whether it looks suspicious, or take signals about user behavior and predict the probability of fraud. The model is not thinking. It is applying learned statistical patterns to new inputs. This matters for security because models can be fooled by inputs that are crafted to push them toward the wrong output, even if those inputs look normal to a human. It also matters because models can be overly confident about predictions, and that confidence can mislead defenders if they treat it like certainty. When you hear machine learning, think probability and pattern, not truth and certainty. That framing helps you answer scenario questions that ask what a defender should do with model outputs. Deep learning is a subset of machine learning that uses multi-layer neural networks to learn more complex representations. The reason deep learning became so important is that it can handle messy data types like images, speech, and large-scale language in a way that earlier approaches struggled with. Deep learning often reduces the need for manual feature engineering, meaning the model can learn useful internal representations automatically from large datasets. That convenience comes with security challenges, because deep learning models can be large, opaque, and sensitive to subtle input changes. It can be hard to explain why a deep model made a decision, which can complicate auditing and trust. It can also be harder to predict how the model will behave on unusual inputs, especially inputs crafted by an attacker. In exam terms, deep learning pushes you to think about interpretability, robustness, and the way complexity increases the attack surface. Complexity is not automatically bad, but it changes what it means to manage risk. Another way to distinguish deep learning is to focus on scale and dependence on data and compute. Deep models often need large amounts of training data and significant computing resources to learn effectively. That means the training pipeline becomes a high-value target, because poisoning the training data or manipulating the training process can alter the model's behavior. It also means the model itself can represent substantial intellectual property, making model theft and unauthorized copying relevant risks. Deep learning systems are often deployed as services, which adds classic security concerns like access control and logging, but also introduces AI-specific concerns like input abuse and model extraction. When deep learning shows up in a security scenario, you should consider both traditional controls and AI-specific threats. The test is likely to ask you to recognize where AI changes the risk profile, not to build or tune the model. Your job is to see the system and the threat landscape clearly. Now we move into generative systems, which are often built on deep learning but behave differently from typical prediction models. A predictive model might answer, "Is this email spam?" while a generative system might produce an email message from scratch. Generative systems can create text, code, images, audio, and more, and they respond to prompts, which are user-provided instructions and context. This prompt-driven interaction is a major reason generative systems are security relevant, because the user is not just providing data, the user is steering behavior. That creates risks like prompt injection, where someone crafts inputs to override instructions, leak information, or cause the system to behave in unsafe ways. It also creates risks around sensitive data exposure, because generative systems can repeat or infer information in ways that surprise people. In plain terms, generative systems are interactive, and interactivity is a big deal for security because it creates a conversation surface attackers can exploit. It helps to recognize that generative systems often operate with uncertain boundaries about what is inside them. A typical machine learning classifier has a clear output space, like spam or not spam, and you can test it across many examples. A generative system has a huge output space, meaning it can produce many different responses, and small changes in prompts can cause big changes in outputs. That variability makes evaluation harder and makes guardrails more important. Guardrails can include policy constraints, filtering, access control, and careful handling of what context the system can see. Even without getting tool-specific, you can understand the principle. The more flexible a system is, the more you need to control what it can access and what it is allowed to do. This is why generative systems often show up in discussions about misuse, abuse, and data spillover. The exam will likely test whether you understand that the system is not just answering questions, it is generating content with potential impact. Another key distinction is that generative systems often rely on large language models, which learn patterns in language at scale and can produce fluent text. The security risk is not only that the output could be wrong, but that it could be convincingly wrong. That matters because users may trust the output and take action based on it, which can create security incidents through misinformation, poor decisions, or unsafe automation. In scenario questions, this might appear as someone using generated output to write code, draft policy, triage alerts, or summarize incidents. The risk isn't just technical, it's socio-technical, meaning it lives at the intersection of system behavior and human behavior. A defender's job is often to reduce the chance that the model's confident tone becomes a substitute for verification. This is why concepts like human oversight and validation matter even when the model is helpful. The test will reward you for understanding that risk is about outcomes, not just mechanics. To map the landscape cleanly, you can think of a spectrum from narrow prediction to open-ended generation. On one end, a model takes specific inputs and produces a limited output, like a score or a label. On the other end, a model can generate complex outputs and appear to reason, even though it is still pattern-based. The farther you move toward open-ended generation, the more the system's behavior becomes shaped by user prompts and context. That shift changes what you secure. For predictive models, you worry about data quality, adversarial inputs, and drift-changing performance over time. For generative models, you also worry about unsafe instructions, prompt manipulation, and accidental disclosure through responses. Both kinds of systems need monitoring and governance, but the monitoring questions differ. Understanding this spectrum helps you read scenario questions faster because you can match the system type to the likely risk type. It's also important to understand that modern systems are often hybrids. A security product might use machine learning to classify events, deep learning to analyze text or network patterns, and a generative model to summarize an incident for a human analyst. Hybrid systems can be powerful, but they combine risks. For example, if the classifier flags the wrong events and the generator summarizes them confidently, you can end up with a very persuasive but incorrect narrative. Or if the generator has access to sensitive logs as context, it might leak details in the wrong place. Hybrid systems also increase the number of places where access controls and auditing matter because data moves across components. In exam terms, hybrids increase the attack surface, and good security thinking involves following the data and identifying where it can be influenced or exposed. You don't need to know exact architectures to reason about this. You just need to think in flows. A beginner-friendly way to reason about AI security is to keep asking 3 questions. What does the system take in? What does it produce? And what is it allowed to access? Inputs can be raw data, features, or prompts, and attackers can manipulate any of them. Outputs can be labels, scores, or generated content, and attackers can use outputs to mislead users or extract information. Access can include training data, internal documents, logs, or tools, and access is where the biggest risks often hide. If you keep those 3 questions in your head, many exam scenarios become easier because you stop thinking about AI as magic and start thinking about it as a system with interfaces. Security lives at interfaces because interfaces are where influence and leakage occur. When you hear a scenario describe an AI feature, try to identify those 3 things quickly. That will guide you to the safest answer choices. Misconceptions are especially common in this landscape, and clearing them up improves your decision-making. One misconception is that AI systems understand meaning the way humans do, so they will naturally know what is safe. Another misconception is that deep learning automatically makes systems more accurate and therefore safer, when in reality more complexity can create more unexpected behavior. A third misconception is that generative systems are just fancy search engines, when they are actually generative and can produce plausible-sounding but incorrect or unsafe outputs. For exam purposes, the safe mindset is to assume uncertainty and require validation. You can appreciate that these systems are useful while still treating them as fallible and influenceable. That balanced mindset is what security education tries to build, because it avoids both blind trust and pointless fear. When you map the AI landscape this way, you also begin to see why the security AI plus objectives are structured as they are. The exam needs you to understand enough about machine learning to interpret model outputs and risks, enough about deep learning to understand scale and complexity, and enough about generative systems to recognize interactive abuse and data leakage concerns. You are building a mental model that lets you answer questions like, what kind of system is this? What could go wrong? And what control best reduces that risk? You are not being asked to implement the system or optimize its training, but you are being asked to make defensible security decisions around it. If you hold onto the spectrum from prediction to generation, and if you keep focusing on inputs, outputs, and access, you will have a reliable way to navigate unfamiliar scenarios. That is what it means to map the landscape, not memorizing every building, but knowing which direction to head and what hazards to watch for.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.